There's still more design to be done. So we're not quite there yet. There's quite a lot to be done, in fact. So first of all, I'll give you a bit of an introduction to phase one, and I've got some maps in a minute to show you what phase one looks like. But we've got civil engineering contractors already in place, and they were given notice to proceed with their designs in early 2020. So now, 2.5 years later, they're making good progress on many fronts, and they have actually started construction work. So, for example, in the Chilterns Tunnel, which is the Chilterns Tunnel is our longest tunnel. It's about 10 miles long. But the tunnel boring machines are making good progress there. They've already completed 4 miles of boring those tunnels. Colne Valley Viaduct is another significant structure on phase one of the project. It's a long viaduct. It's about 2 miles long, and the foundations and the pier construction are underway and ongoing. And in fact, the deck itself has just recently started to be launched. Long Itchington Tunnel, should I say, is a short tunnel. It's only about 1 mile long, but that has actually already been broken through from the TBM, and the first breakthrough, if you like, from the first tunnel bore. Northolt Tunnel is one of the tunnels in the sort of London suburban area between Old Oak Common and West Ruislip, and the TBM for that tunnel launches soon. And we've got another tunnel, Euston Tunnel, which goes right under the centre of London, and that's not started yet. Then in the way of the stations, so there are 4 stations contracts for Euston, Old Oak Common, Curzon Street and Birmingham Interchange. And they're all these contracts have been let and are advanced with their designs, some more than others. Old Oak Common is the furthest ahead and making good progress with advanced designs. And Euston and Curzon Street stations a little bit more recently awarded, and they are progressing well with their designs as well. As far as the rail systems contracts are concerned, there are 3 geographical track work packages on phase one, and they are currently being tendered. We're in the middle of the tender process for those. And there are also supply contracts, and the precast slab track design and supply contract has been in place since early 2021. And switches and crossings and rail supply are also in the procurement stage at the moment. And this just gives you an image of the packages. So you can see the geographical packages for phase one and phase 2A, which is the other phase, which has also got approval to go forward with, and the material supply contracts, they're shown in orange. So looking at phase one and going from right to left, so we've got London Euston Station, which is currently a 10 platform station. And going towards the left, we've got the Euston Tunnel, Old Oak Common Station, which is a station box, Northolt Tunnel, then West Ruislip Sidings, Colne Valley Viaduct, and then Chilterns Tunnel. And that's the urban, the London end of the urban section. And then we go forward on the high speed on the open section through and past Calvert Infrastructure Maintenance Depot, onto Birmingham Interchange before we reach the junction to Birmingham Curzon Street. And you've got Washford Heath Depot, which is part of which is the rolling stock depot, which is quite close to Birmingham Curzon Street, as you can see there. And that depot area, Bromford Tunnel and the Curzon Street Station, are all within the urban area as well. and the remainder are split up into central and north, with north going on with connections to the east, and also straight on to phase 2A and to Handsacre Junction. Now, the connection to Handsacre Junction onto the West Coast Main Line enables services to run to Stafford, Stoke and Macclesfield in the future, and the services from London Euston going up through phase 2A will go on to Crewe and to other destinations to the north. This is phase 2A, still being in the design stage. This one is further behind than phase 1, but it shows you the layout there. We've got another infrastructure maintenance base at Stone, and then we've got a couple of tunnels and a junction again with the West Coast Main Line to Crewe, with the leg going towards phase 2B, which is still yet to gain hybrid bill approval. So phase 2B, so you can see phase 1 in the dark blue at the bottom of this map, and then going further to the north, you've got the orange, which is the western leg, which I say is going through the hybrid build stage, and then the green, which is the eastern leg, which is currently still under development. And on phase 2B, the western leg, the current track form configuration considers slab in Crewe Tunnel, slab from Manchester Airport Station to Piccadilly Station, including Manchester Tunnel, and possibly ballast in the rest of the route. But this is still yet to be decided whether it will be ballast on or slab track in this section. But for the western leg, the current environmental mitigations consider slab track along the whole route as the worst case for hybrid bill. Okay, so the route alignment design and requirements. So first of all, the route alignment is future-proofed for and up to a maximum speed of 400 kilometers per hour. And the civils designs, so the structures and earthworks, are also future-proofed for up to 400 kilometers per hour. But the individual track alignments will be designed for speeds up to a maximum of 360 kilometers per hour. And that is currently the maximum speed, maximum operating speed that we are looking at. That could be under review in the future, but it currently is the 360 is the speed that we're working to at the moment. The design of the track alignment is required to meet the sponsor's requirements and stakeholders' needs for the delivery of the HS2 train service specification and target journey times across all phases. The design solutions for the track alignment shall promote the safety of the rail workers, passengers and members of the public from construction, operation and maintenance of HS2 infrastructure, provide the means for best practical vehicle dynamic behaviour, provide an alignment which has the best practicable passenger experience in terms of good passenger comfort through controlling the application of cant efficiency and rate of change of cant efficiency. And also to evaluate the effect that consecutive and concurrent geometrical elements have on the potential train behaviour as it travels through the alignment. So for the track alignment design, I have some parameters here, which are not all of them, but just ones that I've chosen to show. So we have a track alignment design, which is subject to desirable and limiting values, which is quite a normal practice. And as I say, here's a selection of the different values which we've currently got in our standards. I won't go through each of these, but yeah, you can see just by looking at that sort of maximum cant efficiency, rate of change, etc. We've got curvature. Just a slide here on gauging design. So the gauges that we have on HS2, we've got actually 4 gauges, which are all a variation, but sort of quite similar, but they've got kind of slight differences. But they're all based around the reference profiles, which you can see at the bottom of the screen here, which are the GC reference profile. So all of our gauges encompass the GC reference profile, and also the G12 reference profile at the lower sector. And the OCS gauges allow for the A 2.1 pantograph head, the length of 1600 millimeters. So our standards include our general track specification, and this the track system is specified, designed, constructed, and commissioned in accordance with the infrastructure technical specification for interoperability. So the TSIs. So this is a track specification which is based on European high-speed TSIs, and although the UK is no longer in Europe, we haven't really significantly changed our standards from that period of time. So we're tweaking the standards as we go, as things emerge, but it's essentially a TSI compliant set of standards. So some of the key requirements are that is to be capable of accommodating earthwork settlements within specified limits. So that's the design of the track, needs to accommodate settlements. To meet noise and vibration requirements in the approach to the track system design, and where necessary specifying additional mitigation measures. To provide a minimum track system design life for 60 years, that's not applicable to rail replacement, but it is for the whole system generally, with minimal requirements for inspection and maintenance in line with as low as reasonably practical principles. To facilitate the locating of command and control signalling equipment, to incorporate proven in service design principles, and to be capable of achieving close construction tolerances, i.e. see the example of the tolerances below. As you can see, they're very close tolerances. So the vertical deviation is +0, -4, and the deviation from the lateral position is ±2 millimeters. So we have a range of 4 millimeters essentially, both in the horizontal and vertical. But there are other tolerances which are specified. This is just ones which I've picked for this slide. So just a slide here on CWR design. Our stress-free temperature, because HS2 is, for the main line, is slab track throughout. We've got an SFT of 24 degrees ±3 degrees. And the SFT in tunnels is different because it's determined as follows. So the SFT in tunnels applies to the length between 2 points, each of which is 40 meters inside the tunnel portals. And the rail, which is given time to acclimatise inside the tunnel to the tunnel temperature before it is it's fixed, and then fastened down, and then the rail temperature at which the rail is fastened down it becomes the tunnel SFT for that location, and it's recorded as such. So the track system design, as I said earlier, on the main line, standard track is precast. Well, it's all slab track, but the standard track is precast slab track throughout most of the open route, and that includes the tunnels, Chiltern tunnels, Long Itchington Wood Tunnel, and the cut and cover tunnels. But in the urban areas, we have a resilient track, but that is yet to be decided in the future due to the need to select a system that meets the acoustic targets that can show that it's proven in service at speeds applicable to the location where it's to be installed and meet the noise and vibration targets as well. And then we have a third track system type, which is special track, which is in terminal station platforms, and that's particularly to allow drainage of the bioreactor waste grey water discharge from under the trains when they're stationary in the platforms. So that track form, go on to talk about that in a bit, but it's gonna have a channel which allows the discharge of that water. And then in depots, mainly depots will be ballasted track with some slab track just at the entrance to the depots. And the sleepers in the depots are likely to be either concrete or composite sleepers. This is still yet to be decided. Other track forms in the depots, typical of depots is embedded track, where you've got sort of a concrete surface at rail level where rubber tired vehicles cross the track inside the depot. And pit inspection roads, like a plinth track, if you like, for inspection underneath the vehicles. So here's a typical cross section for the precast track, and what you'll notice there is provision for 3 trough routes on each side. Here inside of the mast, we had a long debate about whether that troughing should be on the inside of the mast or the outside in the cess. We have provided 3 on each side, but it's not always going to be 3 on each side. There's going to be a reduction in some places where it's not required. So yeah, so that's just really the sort of worst case scenario. And this is the cross section in a cutting on straight and level track. So it shows you the drainage on the outside, because this is in a cutting. You've got some drains beyond the walkways. Cross section on canted track. Just to give you an idea here, the 2 low rails are roughly the same level, and that you end up with a sort of channel in the middle. And in a cutting scenario, this means that you've got to have drainage from the centre of the tracks out to the cess, as shown there. So our standard track, which is precast track, and I mentioned earlier that the precast contract has been in place for some time now. And some of the benefits of having precast track is that there's a 15-month program opportunity for phase 1 route, which because of the way in which we've procured our contracts, we've been able to award a precast contract very early before the track contractors come on board, and this allows for the production of the precast units to be done so that we can get a good sort of gain on the program, so that when the track contractor comes on and does his design and starts getting into construction, this activity can be very much well underway and mature. So so that's one of the advantages. Another one is the quality control and site construction environmental factors. With casting these precast units in a factory environment, there are a number of benefits to doing that with quality control and also for carbon reduction. And also when it comes to in years and years to come, if we need to replace the track system, removing precast units as opposed to in situ concrete will, in our minds, be easier to do that. So the replacement methodology is more efficient with the precast. And here's an example of VCE and POR. VCE are a consultant to POR, who POR are providing the precast units, and they are providing 3D BIM models, so that we can see exactly where all of these units are going to go, according to the changes all the way along the track. So you can see an example there on the left-hand side of a detailed design, how that will look in the BIM environment, and the schematics that they're providing also for the route-wide models on the right-hand side. A little bit about the surrounding interfaces, if you like, to the precast design. First of all, the precast, it sits on the on a grouting layer and also on the concrete bound layer. Each unit sits on that and is tied into with reinforcement keying into the units, and that sits on a protection layer underneath the CBL, and the bearing capacity of the protection layer is 120 meganewtons per meter squared, which is a very solid base. That's the requirement for the earthworks to be compacted to that level. That's underneath. On top of the units, we've got cable crossings on top and between the joints. So where the smaller cables go across the track under the rails, they can go threaded between the joint, between each slab, and there's a 40 millimeter nominal gap, but it can be up to 280 millimeters where necessary for where a larger gap is needed for cable crossings. Where cable crossings need to go under the track, they can go in the intermediate layer, but up to a minimum of 100 millimeter thickness above the crossing itself is necessary. So, and then of course cable crossings on the slab surface where there's very small sort of like bonding cables can just go under the rail and be pinned to the top surface of the slab as well. And some further equipment on the slab. So some examples here, and this shows you some bonding cables on the left image, and in the middle you've got the Belize equipment, which is for the CCS, the signalling equipment. There are Belizes that need to be fixed to in between the rails every so often, and the green areas below on this slide show the drilling zones, which allow you to or allow the other rail systems contractors to be able to drill the slab in the correct position, so they're not drilling and touching the reinforcement. And there's a couple of examples there of equipment that need to be fitted in between the slabs and on top. Curvature for the precast units, the geometry of the alignment is fed into a computer which controls the casting of the units, and where curved units need to be provided, they are cast so that each unit is got its own location along the track, and the radius of the curve is cast into the slab, and where there's a transition curve, the radius, there's a radius which is an optimal radius which is cast in, and then there's a slight variation to the position of the rail which is created by the insulators, having different insulators between the rail and the shoulder of the fastening. In terms of the vertical, there is allowance for settlement and heave, which is possible with the precast the slab track units, and that can be corrected by using a number of different ways, but this is one way where the packings can be inserted underneath the a base plate, and the fastenings, as you can see there, will allow for a vertical reserve of 70 millimeters, or up to a maximum of 70 millimeters, and plus or minus 10 millimeters laterally in a horizontal direction. There are some special fastenings where there's an interface between the earthworks and the structure. So in this particular case, you can see that there are different fastenings across this joint between the abutment and the deck of the bridge, and that allows for longitudinal movement of the structure to move so that the rail is allowed to stay locked in and fixed, but the fastenings will creep backwards and forwards with the contraction and expansion of the bridge deck. And we also have some structures which are on the skew, and there has to be some allowance for some very small movements laterally according to the movement due to the skew of the bridge, and that's restricted to 2.5 millimeters lateral movement, which is accommodated by using special fastenings, but over a longer distance than what is shown here. On viaducts, there's a need to accommodate, particularly on our longer viaducts, some very long gaps for expansion of the viaduct, and there's a need to actually fix the structures on either side that's supporting the rail to give it stability over such a large gap. Where there is a very small gap, because the structure is very small, or the span that's expanding is very small, then there's not so much of a need to do this. But this is a concept illustration of rail support method, which is used in Europe, and we're anticipating having these sort of arrangements on HS2 when our designer comes on board and looks in more detail about that. Just slide on transitions to tunnels. There are transition units in the precast range, but they are fairly consistent. They don't really change too much. But the main transition detail that's going on is underneath the precast slabs, in the concrete bearing layer and underneath in the protection layer, as the earthworks usually are cutting interfaces with the tunnel structure, and there's usually a portal slab or structure outside of the tunnel portal itself, which is designed to have a transition to allow the change of track stiffness between the tunnel and the outside of the tunnel. So this is just gives you an idea of the image of a completed system of the precast, and this is actually an example of the special fastenings you can see in yellow here at the end of the viaduct to allow movement through the curve, to allow some free movement of the rail. I think these are zero toe load fastenings, the yellow ones, and the ones nearer to the front of the camera are fixed. So just a slide on resilient track, although still yet to be decided what the resilient track form will be, because there's a need to select a system that meets the acoustic targets and show that it's proven in service, and that kind of narrows it down to a number of different systems. But there are possible options like a booty block system, as shown in the sketch, or a slab track system which has got sufficiently resilient elements. But this is all still to be decided. There could be even another one which is proposed once we get our track contractors in place who are doing the design for this. But Yep. Okay, that's still outstanding. So just a note on sound, noise, and vibration. So the, the in the tunnels and the urban locations, there is more of a concern about ground-borne noise, and we've got two levels of mitigation, which, depending on the receptors and what areas we are, if there's any sensitive areas for sound, noise, and vibration, depends on the level of mitigation that's needed, and that will need to be studied in the future. And that's mainly the urban areas that we've got that requirement. In the open route, there are requirements for airborne noise to be mitigated, and we have noise barriers and matting in places. Yeah, so that's basically still yet to be decided exactly, but we have the civils contractors erecting noise barriers in places where they have carried out studies and found that they're needed in those places. Track drainage design, just showing you here, this is the cross section on an embankment, and it shows at the top where you've got straight and level track. The surface water drainage falls from the centre towards the outside. So water will fall from the middle and go in between the precast slabs and continue to fall to the outside and then away to the sides of the embankment, or if it's a cutting, it will be to the drainage in the cess. But where we have curved track, there's a need to drain the centre between the two tracks because of the profiles that we've got, and therefore there's central drainage on curved track with inspection chambers to drain the surface out to the outsides. Bioreactor waste drainage, I've already mentioned that this is it's evident actually at Euston and Curzon Street stations, where they are terminal stations, and because of the nature of the service, the frequency to empty the tanks in the depots for all the time, there was a need to be able to empty the tanks at other locations, and it was decided to do it in this way, by treating the waste from the toilets in the trains and filtering and treating them on board, and then discharging them into a drainage system which is in the track in the platforms. So you can see from the images on the right, there's a typical bioreactor arrangement, which would be on the train discharging into the track. And then on the right, it shows you the two options where you're in a depot situation, it goes into an intermediate tank and then into a drain, as opposed to in the track, which is also shown there. So the urban track contractor will be required to design a suitable track drainage system for this when they come on board. And the following are some design factors. The water quality has got high salt content, mildly corrosive to steel and concrete. It contains ammonium liquid. So a track line is going to be required. Thames Water Authority has confirmed that discharging the water into their system is okay, and overnight discharge will only take place overnight, so passengers won't be seeing that taking place, because that the trains will be out of operation when that happens, and the capacity is about 200 litres per carriage per day. Switches and crossings designs. So we've got two types of S&C. We've got the high-speed S&C, which has got some very long turnouts. Some high-speed turnouts are over 125 metres long. And then we've got a whole range of low-speed turnouts as well. And these are basically UIC turnouts to the European standards, which many people are familiar with, many projects. And the S&C itself will be one of two options. It will either be on in situ or on precast. We've still got a design that's going to be done in the future around this to determine this. Some are mandated to be on precast units, but there will be others that could be either in situ or precast. And this gives you an idea of the sort of typical layout in S&C, how that might look with the two types. In terms of the geometry of the S&C, we've chosen from a long time back a particular geometry which has got clothoid transitions included in the lead of the S&C to enable good passenger comfort, to minimise the jerk as the vehicle passes through the diverging path of the S&C. In some cases is a double clothoid, and in others we've got just a single clothoid at the switch entry going into the turnout, depending on the design of the S&C. But those diagrams there give you an idea of the smoothness of the lateral acceleration as a vehicle goes into the diverging path, which avoids an abrupt change of direction, which you would otherwise get with a circular, like a conventional S&C geometry. Rail expansion devices. So POR have been looking at our RED designs, although we've still got more to do on this in the future. But they've performed some studies on these, and there's a possibility of incorporating slab track on the rail expansion device system itself. There's at least that's been established. And REDs are normally combined with a special structure to bridge the gap to limit the rail support distance to the predefined maximum value of 650 millimeters. So this is required in order to limit the rail deflection of rail passenger traffic and the bending stresses in the rail profile. And possible solutions for this also applicability of solutions to be defined case by case basis, depending on the expansion joint, space requirements, anchorage forces, drainage, etc. Okay, so that's it actually. Thanks for listening. And if you've got any questions, I'm happy to try and answer them as best as I can.
Okay, Phil, well, thank you for that. If anyone's got any questions, obviously put them in the chat. There is a question or two there, but just a question for me, Phil. Obviously, with the line speed of 360 kilometers an hour, which is rough and dirty 225 miles an hour, is there a restriction as the trains go through the tunnels? And if so, what line speed is expected there?
There are tunnels where the speed is restricted, but not because of the tunnel. The tunnel, we do have 360 through Chiltern Tunnel,
Right.
And that tunnel's 10 miles long. So yeah, no, there are, I mean, traditionally restrictions are placed in tunnels where they're not designed for the piston effect, if you like, running into the tunnel. But we do have porous portals on HS2, which allow for the piston effect to be dissipated as the train enters the tunnel. So no, the design accommodates the 360 in the tunnel. So there is no restriction in theory needed for our fastest speed tunnels.
Okay, thank you for that. Just looking at the chat, there's a couple of questions here. Questions been asked about the slab track being used in the tunnels. is that going to be the same that will be used on the open route in phase 1 and 2A?
They are slightly different. They're pretty much the same envelope or the same footprint, if you like, as they are in the open route. But some of the tunnels have a drainage system which runs in between the rails and the forefoot, and because of that, there is a need for inspection chambers every so often throughout the tunnel, and therefore there is a special precast unit which has got an additional cutout for the inspection chamber to be accommodated in the slab units. So they are slightly different, but not generally different. They're just the odd one here and there for drainage.
Okay. A couple of other questions. What ERTMS level will be used?
It's level 2.
Level 2.
Level
And
2.
what's the
Yeah, I
maximum?
mean, the level 2 is in-cab signalling, but not moving block, which is level 3. So we are on level 2. So
Okay.
this is why we've got the Blazes. Well, I'm not a signalling engineer actually, so I'm probably getting out of my desk by saying that, but it is level 2 anyway. Yeah.
Okay. Another question is, and I don't know if you know the answer, what is the maximum noise level allowed for HS2?
Well, that does depend on the receptor, and also we do have, well, we have graphs in our standards, but it's not, there's not one answer to that, to be honest. It depends on a number of factors, but I'm afraid you have to look at a graph if you want to know the answer to that, and you have to study what the requirements are, the environmental requirements for a particular receptor where the railway passes beneath, in order to determine that. So there's no one answer to that, I'm afraid, and I'm not probably the best person to answer the ins and outs of that. Yeah.
Okay. Comment here in regards to grey water, is 200 litres per carriage or per train set?
Per train set. Yes, per train set, I believe.
Okay. And another question here. It says, would you be able to share any further information regarding the design considerations over transitions, particularly the effect on the individual slab units?
Yeah, so as I understand it, there is a optimum radii cast into the slab for a particular section of the transition, and then the actual transition itself is achieved by having different sizes of insulator, which positions the foot of the rail to the correct position. Yeah, and that's pretty much, as I understand it, how it works.
Okay. And then another one from yourself, you mentioned noise mitigation, and traditionally on like HS1 we have acoustic barriers, but you also mentioned matting. So in what situation do you use matting over an acoustic barrier?
I think that's where the noise mitigation is lower and a dampening of the vibration of the rail is sufficient. So there's a matting which it dampens the noise, and also what's being looked at is matting between, where noise can reflect off of the slab. The matting can break up the reflection of the noise.
Gotcha.
So yeah, so there's different solutions out there, but it's still the design is still in its infancy actually, as to what we're going to end up with. But yeah, these are things that we're just currently looking at the moment.
Okay. Just to answer the question, the Phil's presentation will be available on the PWI website. It might take a week or two to get uploaded, but yes, it will be available shortly. And then Harry Jones has asked a question: what was the rationale for using slab track? Japan uses traditional ballast. Why slab track?
Yeah, Japan does use ballast, but it also uses the J slab, which is the precast slab track as well. But we chose slab track because of the fact that we're going to have such an intense service on HS2 that we would not have time to do the maintenance that's required for ballasted track with the tamping, etc. So what we really needed for a high capacity railway was a very low maintenance railway, and there are benefits in maintenance for having slab track long term, and you can argue that it's an investment. The capital expenditure is higher, but you get a benefit from the OPEX operational expenditure in the long term. But it was, I mean, although that was a consideration, it was really about the fact that we won't have the window to shut the railway down to do the level of maintenance that's required with the intensity of service that we need. So that's that was a decision taken a long time ago. I'm not sure it's environmentally reckless. You know, I mean, the precast units can be cast in a factory environment using green electricity. So the carbon footprint of the precast, we are working towards trying to reduce that carbon footprint for precast. And of course, ballast has a carbon footprint as well in terms of quarrying and shipping ballast and moving it across the country as well. So I'm not sure that there's a strong case for ballast from an environmental point of view, and using precast from a concrete point of view does. I mean, certainly concrete is being looked at now from the point of view of using different replacement materials for concrete to reduce the carbon footprint, and that together with the precast design is something that we can look at to actually try and reduce the carbon footprint. So yeah, I'm not an expert on these environmental points, but this is what I understand, and I think there's not a clear case that ballasted track is environmentally much more superior to slab track for those reasons. So I hope that sort of kind of answered your question, Harry. Yeah.
Okay.
Yeah.
I don't think there's any other questions. Harry, did Harry want to say something there, or?
Oh, I was just going to chip in actually. Peter here. Phil, that was quite a fascinating, detailed presentation. Thank you very much indeed. I'd just like to propose a vote of thanks from the audience that has been listening in today. You've obviously put a lot of effort into that, and it's been truly appreciated by the audience. So thank you very much indeed.
Yeah, thanks, Peter. Yeah, appreciate that. Thanks very much.
Thanks, Phil.
Yeah, thank you very much. Very interesting.
Yeah, thank you. Thank you, everybody.
So just to conclude, Peter, thank you for doing that. Phil,